We ended the last class meeting on the NIOSH lifting equation, looking at one particular job, a package inspection task. This is on page 12 in your workbook, and recall the page 12 is listed at the top of the page, RWL page 12. It is actually page 92 in your workbook, but within this section on the NIOSH lifting equation, the pages are numbered at the top. You'll see those appearing frequently. But on page 92, 93, we were looking at the package inspection task in which an employee lifted a package from a lower shelf, shelf 1, where they were reaching 10 inches in front of them at a vertical location. Their hands were 22 inches high off the floor. They inspected the package, they picked it up, and then they put it on the higher shelf 2, reaching forward 20 inches, and that's the distance between their ankles and their hands on the package. And then they have a new vertical location of their hands at 59 inches. They were lifting at a rate of 3 lifts per minute for a 45-minute task duration. You can see the height of the second shelf indicates they cannot step forward, and so they have to reach out to put the package down. And since they've inspected the package, they don't want to damage it, drop it, cause any problems to it. It's good quality. They are careful when they put it down on the second higher shelf, and so that means they're using significant control at the destination, the end of the lift, whenever they put the package down, meaning we need to analyze the end of the lift. From page 12, we filled in the job analysis worksheet, or JA, on page 13. The top part, reminder, I always want you to fill out the top part, that background information, so you don't lose that. I'll check it on the exam, but I'm not going to check it for correctness. And so we filled in the shipping department. You might have had quality control department. Job title, we said package inspector. If you put lifter, if you put material handler, any of those would have been fine. Your name, the date is today's date, and a brief job description. From that, we went into step 1. On a word problem, you'll need to find those variables in either the job description or from the picture itself. We looked at the object weight. The package he was inspecting was 26 pounds. We counted as both the average and the maximum since he's doing the same task. The hand location was reaching ahead horizontally 10 inches. Vertically, his hands were 22 inches high off the floor when he picked it up at the origin. At the destination, he was reaching ahead 20 inches with a vertical location of 59, which means the package vertically moved from 22 up to 59. Subtracting those two, absolute value was left 37 inches. That it traveled, the distance it traveled. He kept everything right in front of his body. He didn't twist his back or twisted his hips or anything, so the asymmetric angle when he picked it up at the origin was 0 degrees. Similarly, destination right in front of his body, so it's 0 degrees of twist. Frequency was 3. Duration in hours was 0.75, so you changed the 45 minutes into an hour. And then object coupling was fair because he could grip his hands, his fingers 90 degrees around the edges of a box. We always go in on step 2 and do the origin because there's always potential risk at the origin. So we filled in for the origin. We went back to the hand location at the origin, 10 inches. We took the 10-inch measurement to the multiplier table and said that for 10 inches H, that means we have an HM of 1.0. We put 1.0 in the HM box at the origin. Right here. Similar, we did VM, where V is 22 inches. Took that to table 2 in the multiplier table and found it was 0.94. And we worked our way through that by looking at a new table for every multiplier variable. After we found all the 6 boxes, we multiplied 51 times 1 times 0.94 and so on to come up with 34.9 pounds is the RWL at the origin. When we go to the destination, we have to make a decision: is there significant control being used when he puts the box down? In this case, we said yes, he doesn't want to damage it, so there is significant control used. Since his muscles are still controlling it precisely, we want to evaluate the risk of this muscular control. And so we'll fill in the boxes for the destination. Our RWL was 51 pounds. For our HM, we have a new H. H at the destination is 20 inches. We take that back to our table 1 multiplier with an H of 20 inches. That means HM is 0.50. Recall the second part of the table is metric. The second half we're not going to be using metric. But at 20 we have 0.50 to fill in our box. For VM, we have a new V is 59 at the destination. We take that to our table 2. 59's not on the table, but we have a 55, a 60 inch. Falls somewhere in between. We see that 59 might be, it has to fall between 7.8 and 0.81. It's closer to 60, which is 0.78. And so we might go 0.79 for our VM. DM, we don't actually have to go and look up again because we've moved 37 inches. 37 inches, it's the same for both the origin and destination since the travel distance between, so we can copy that 0.87. For AM, we have a 0-degree twist at the destination, so we could go back and look up 0 degrees. This just happens to be the same amount of twisting, no twisting. So by coincidence, it is a 1.0 again. Frequency again, we have 3 lifts per minute for less than an hour with a vertical at the origin of 22. Going back, since it is the V at the origin always, we had 3 lifts per minute. We had less than an hour. V was less than 30, so we still have 0.88. So actually your FM will always be the same between the origin and destination. Lastly, we have coupling. Coupling is fair, but the coupling will depend on this little note you made to yourself. V is at the location or origin or destination you're evaluating. We're now evaluating the destination. The destination V is 59 inches, and so 59, if it's fair, 59 is greater than 30, and so we're in this column here. And so we can see that our, even though it's fair, the FM has changed to 1.0. And so that one's pretty tricky. Be careful. Be careful on that one. Your CM can change even though the coupling is still fair. Once you get those, you multiply all the boxes together. Don't forget the 51 pounds. Multiply all those together, you'll come up with 15.4 as the RWL at the destination. And so now step 2 is done. We move on to the final step in the handout or on the job analysis worksheet, and that's to calculate the lifting index. In this case, lifting index, the equation is the object weight. Our object actually weighed 26 pounds, and so you can put that in for both the origin and destination. And then the object weight is divided by the RWL of the location. And so lifting index at the origin was 26 pounds divided by RWL at the origin was 34.9. Divide those, you'll come up with a value of 0.74. At the destination, 26 pounds divided by the destination RWL is now 15.4. So 26 divided by 15.4. Put that in your calculator, you'll come up with a 1.69 or 1.7 as your destination lifting index. Okay. Once you've got all the job analysis worksheet completed, now it comes down to interpretation. So what does this mean? And so the meaning on this goes back to RWL page 4, step 3. If you turn to that, I've got some of it typed in for you on RWL page 4, step 3. Some of it you might want to add in as we cover it. But basically, the lifting index, what it's meant to be, is an index of physical stress. And if you think, does your body want high stress or low stress, you're going to say low. And so low LIs are good, high lifting indices are bad. And how you know low or high? Well, the cutoff is going to be 1. If the lifting index is less than or equal to 1, so don't forget the equal to, less than or equal to 1, then the task is low risk for most people. And so most people can lift an object at the given frequency, at the locations, origin, and destination you've specified in the problem. Most people can lift that with very low minimal risk of injury. And so in that case, we consider the job is okay. You do not have to redesign it. It's good to go. You don't expect to see injuries in that task. However, if the lifting index is greater than 1, so it's 1.2, 1.7, 3.5, so if it's greater than 1, then you want to redesign the task because the risk of low back pain is present. If the lifting index is greater than 1, you would expect to see some injuries. Injuries may occur. And so then we need to look at how do we control the job so that these injuries don't occur if the lifting index is greater than 1. And just, basically this is saying the weight is too much, and so what can you do to control the job to make the job better? And so one thing you want to consider, if it's a high hazard lift, and high hazard is defined at a lifting index greater than 3. If it's a high hazard task, you want to eliminate the lift. And so a way to eliminate it, to totally remove the human from the lifting part, is to use a lifting device. And so you can use hoists, cranes, vacuum lifts, your dollies, forklifts. Any of those types of devices will remove the human from the lifting part, and so that would protect their back from injury. If the job's not that much, that high, that bad, you might not want to implement such an expensive lifting device. And so alternatives, if the lifting index is lower than 3, is to, one way is to reduce the weight to a low risk weight. So reduce the weight to a low risk weight. In this case, you calculated an RWL 34.9, an RWL of 15.4 at the destination. You would need to go with what is the low risk weight in this task? Okay, so we'll need to determine that. Another option is to prioritize the multipliers, meaning rank them from the smallest to the largest, and control beginning with the top priority. And so we'll look at the multipliers of the job, all those little boxes that you filled in. We're going to look at the location that's particularly hazardous, and you're going to start controlling those by the worst thing in the job. And so which multiplier is the worst? Move on to the second worst, the third worst, and so you're simply just ranking them from smallest to largest, so 1 to 6. Last resort, if you don't change the job, if you can't physically engineer it out or use a lifting device, then last resort is a team lift. And I think we discussed this during class. It's a team lift is a last resort, and this is ergonomically speaking, because team lifts are difficult. People are not often trained on team lift. Team lifting requires communication, coordination. And you imagine yourself, you've lifted, a couch or a bed or something. You have one person lifting before the other. You have one person who takes more weight on. There's some delay. There's just, kind of a lack of coordination. That one person always gets more of the load. And so we can't assume that a team lift means they're lifting equally. Okay, so going back to reducing the weight to low risk. Reducing the weight to low risk. We have an RWL at the origin is equal to 34.9. RWL at the destination is equal to 15.4. And so we want to know how much weight is safe. Essentially, we have to go with the lower RWL. And I'll put that equivalent to what we would identify as being the safe weight for the task. If we can get the weight down to 15.4, it will be safe at the origin. It will be safe at the destination. And I see that I've got 15.4, 15.2 down here. Don't worry, the 0.2, your body's not going to feel the 0.2, and so I might have used a different 0.8 something for 7.9, I think, for my VM. So don't worry about that. So we need to go with the lower weight if we're going to control the job by weight. And so we look at how do we get the weight down to 15.4 pounds. If it's now at 34.9, we can get it down to 15.4 by putting less items in the box, or by reducing the weight of the box itself, the weight of the container. And so you can look at, are there options? If not, if you can't get it down to 15.4, then we have to go back and can we change the multipliers? And that's where this slide is. On this, we want to look at the worst location. Worst locations indicated by the lifting index. Lifting index, higher is bad. Higher was the destination. And so in this case, lifting index was 0.74. Lifting index was 1.69. The 1.69 is a problem. It's greater than 1. And so we want to focus on controlling the destination as being our primary location of interest. If we go back and look at what multipliers the first, we had to rank them from lowest, smallest to highest. And so on the multipliers, we're going to give we're going to assign a rank of 1 to the lowest value, which is 0.5. The second lowest will be 0.78. Numerically, the third lowest is 0.87. And then 0.88 will be our next lowest. The ones you can't do anything about, they're as good as they can be. You're only going to have the highest value you can have is 1. And so you can ignore those ones. But starting out with 1. 1 refers to this. 1 refers to the HM at the destination. And so we can see a person has to reach out 20 inches. How do you stop them from reaching out 20 inches? You want them to reach out 10, 15, 12, 11, so smaller amount than 20 inches. And so at this point, you just look practically at the job. How can you reduce it 20 inches? And you're going to say that one way is, well, what if we extend this shelf out? Okay, that would work. You'd extend it out a little bit, you extend it out a lot, that would work. If you can extend it out, could you chop off the lower shelf? So chop it off so that they can step forward to lift the box. Okay. Those you may or may not be able to do. If it's an assembly line, if it's something coming on a conveyor here, coming on a conveyor to be taken away, if it's that, you might not be able to push those around. You might not be able to move them without creating a large expense, without shutting down, that line, and so that may or may not be feasible. If it is, wonderful. If it is not, then you move on to number 2. Number 2 relates to the vertical location of the hands at the destination. That refers to this vertical location here, 59 inches. And so you look at how can we make that better? And you would probably tell me, well, let's reduce the height of the shelf. Instead of it being 59 inches, can we only make it 35 or 30? And again, you're going to need to decide, is that possible at your job task? If it's not possible, you move to number 3. Number 3 refers to the distance you've moved. So this total distance here. And you could see that you might be able to move up, raise the bottom shelf and or lower the top shelf. If they're feasible, wonderful. If it's not feasible, then maybe you need to move on to, number 4, which is frequency. Frequency, you can change the duration, but here it's already low. It's less than 1 hour, so it's already low. Or you can change the 3 lifts per minute. Just realize that anytime you're decreasing frequency, you're slowing down productivity, you're slowing down the production line. And management, owners of the company, shareholders, and so on, they're not very happy if you slow the job down. And so in that case, the frequency multiplier is something that's practically somewhat difficult to change. You might be able to add in some job rotation so that he does 2 of the lifts, somebody else does 1 of the lifts, but otherwise it might be difficult to do. You have a page within the handout, within the RWL handout, that identifies how you can do some changes. If it wasn't obvious, it wasn't common sense, if it wasn't practical, RWL page 8 contains suggestions for how to change each of the multipliers, and so you can look through that. Now we're going to start example 2. I'm going to move that to a new recording. I would like you to practice this one also, but I want to give you some time to take a look at it yourself. In this case, we're moving a roll from a cart, putting it down into a machine. And so go ahead and give that a try, and I'll come back and do another lecture on how to solve that problem.